you penultimate?
Second penultimate.
Pen, pineapple, apple pen?
Thanks for catching that. There. Does that change everything? You can hear me now? They can't hear you scream in space. No one can, in space, nobody can hear my, that I had the wrong device. Muted or no Pamela around. Okay, there you go. Yeah, I know. At some point my computer hiccuped, and I think it it did a Windows update. And
oh, did you? Oh, you have a Windows update problem.
That Windows update.
Yeah. And then everything.
Otherwise known as why you use Linux. But
oh, yeah. I always have this romantic notion. Every 10 years or so, I go, that's it. I'm going to install Linux, and then it's just misery, and then I just go back to Windows. Well,
you know how you can tell someone uses Linux.
They tell you. Also,
I work in Silicon Valley.
Yeah. Also that they do CrossFit. Yeah. Yeah. No, I'm waiting. Actually, the thing that I did that was kind of fun. I had a Chromebook, and you can dual boot it into Ubuntu, and that's kind of cool because then you can also abandon it the moment it starts to malfunction, and then just go back and forth.
You can always just go for a Mac.
Yeah. I mean, the Mac has problems too. I used to run Mac, and now I got sick of the Mac too. I'm fine with Windows.
The old joke, How many Mac users does it take to change a light bulb? None. When the light burns out, you buy a new house.
Right. Oh, sounds about right.
Feeling called out today. Feeling called out.
Are you the Mac user?
I am when I'm down here. Yeah. My upstairs is a Windows box, but this is a MacBook.
Right. Yeah. No. They sort of lost it. They sort of went through a lot of bad machines back on the MacBook Pro fairly recently. So, yeah. No. I like although my computer's getting really old. Actually, it's constantly complaining that my bit rate isn't quite fast. It's saying that my audio. Oh, okay, I fixed it. Okay, good. This computer is starting to chug, trying to do the live streaming. So I may need to stick a faster something in it.
Yeah.
I don't know what would be probably a faster processor. I mean, that's a great thing about PCs is you can just pull out the chip, put in a new chip, move on. So can't do that with a Mac where even the RAM is welded to the motherboard.
Yeah, it is a one-box system. I call them great grandma computers. You give them to your grandma; she can't mess it up.
Well, that's the Chromebook. I tell everybody to get a Chromebook.
That's the new solution, but back in the day.
All right, I'm going to say hi to a bunch of people. I forgot to do that. Hello to Andrew Planet, A.B. Scott and Flower, Bob Moeller, Brexit Denier, Corey S., David Dunn, David Fairweather, Eric Knapp, Frank Tippin, Hal McKinney, Horizon Brave, Ian Farquharon, Larry Beckham, Derry King, Luke Wilhelm, Nancy Graziano, Neil Yu, Nifty, Paranor, Arjone, Sergio Botero, Sergusi, Tesla Ranger, Trey Harmon, Uncle Bill Druin, Visto Tootie, and Zapvan. Hey, everybody. All right, let's get started. Enough of this shenanigans. All right, there's me. Here's my intro. And here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, June 17th, 2020. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about, finally, a mission to Neptune. Evidence building that the Standard Model is incomplete and a rare ring galaxy seen in the early universe. Joining me this week on my screen is Brian Coberline. Brian, welcome back.
Hi, everybody. It's good to be here again.
And we've got, Chris.
Greetings.
Chris Carr, how's it going?
Doing well.
You've got a sort of a sneak preview of what you're going to be talking about on behind you, but we won't go into any more detail until we get to your segment. But I
thought I'd use the background as an assistant.
Yeah, no, I think this is great. Actually, I'm pretty stoked on this idea that people are taking pictures and putting them as their background. Speaking of backgrounds and things we're going to be talking about, we've got Beth Johnson. Hey, Beth.
Hey, how's it going, Fraser?
Good. Again, I mean, spoiler alert, you're going to be talking about Neptune. But until that point, I just want to give everybody a reminder that if you want to be part of this incredible community, go to the Weekly Space Hangout crew. That's wshcrew.space. They will hook you up. They'll give you your executive producer privileges, and so that you can invite cool guests onto the show. And just a reminder that we've only got 2 more episodes before we go on to our summer hiatus. So next week's episode, and then the episode after that, and then we will be gone until September. So you really should. Now is your chance. If you want like a bookmark into all things Weekly Space Hangout, you should make sure that you join the crew, wshcrew.space. And speaking of interesting guests, this week we've got Dana Backman. Dana, welcome to the Weekly Space Hangout.
Thank you for the invitation.
All right, so who are you? What do you do?
I am an astronomer who is spending all of my time recruiting and training high school teachers to fly on the NASA Flying Observatory Sophia so they can see the scientific process and take that back to their classrooms. And that is a lot of fun.
Sophia is easily one of my favorite missions. A gigantic infrared telescope bolted onto the side of an airplane that just flies around and takes pictures of the sky. I love it. What is this? So what is the process if you are a high school teacher and you want to participate in this? How does it work?
What you need to do, NASA has asked us to recruit districts rather than individual teachers. So what you need to do if you're excited by this is get your school district science coordinator to contact me, and I'm D. Backman at SETI.org. You can find that, I suppose, somehow. But anyway, go to the SETI Institute's website and look for AAA, Airborne Astronomy Ambassadors, and you will see how to contact us. Anyway, you need to get your district to talk to us about getting a memo of understanding, and then we will work with them to recruit teachers from your district. And I'm happy to say, starting next year, that we're extending to middle school and to community colleges. So it's been high school up to this point, but now we're extending the age range. But anyway, the first step is to get your district talking to us, and then we'll be selecting the 2021 teachers in the fall of 2020.
Right. And what is what's the commitment if you want to be a part of one of these missions? How does the whole thing work?
You sign on for a 6-month series of webinars where we train you in what to expect, what's going to happen, why Sophia works the way it does. Then we give you a summer face-to-face workshop where we train you in the curriculum module that we want you to have in your classroom after your flights. So it's a 2-week curriculum based on NASA materials that the teachers are committed to teach in the school year after their flights. And then you have committed to a week away from your school to come out to California to fly on Sophia.
And I know that Sophia flies from a bunch of places, from New Zealand sometimes, from California sometimes, Europe sometimes. And so how long will an actual flight take if you actually...
10 hours. It's an all-night flight, and we do our best, Sophia's schedule notwithstanding, to get the teachers to fly twice during the week. And our teachers are always flying out of Southern California, the main Sophia's home base, right?
And what kinds of scientific missions is Sophia, normally going to look at?
Well, it's a general scientific observatory, so the astronomers apply to look at planets, stars, galaxies, star-forming regions, you name it. Sophia is not particularly a cosmological tool, but anything else out to nearby galaxies and all the way into the moon. Astronomers apply for time on it, just like on a regular ground-based observatory or the Hubble Space Telescope. So could be anything, a mix of things on a given night.
And so then, like, just trying to understand, like, for the experience of the teacher, I mean, obviously the telescope is in its own separate compartment of the airplane. The airplane is flying around in circles, doing its observations.
Zigzags.
Zigzags, yeah. At as calm and stable an altitude as possible. So what kinds of activities, like, what do the teachers do? Are they roaming around? Are they looking over people's shoulders? Are they learning?
Yes. We have our own dedicated console, which when this was originally envisioned, when the Sophia project had its inception in '96, there was a console designed in for the teachers to sit at where we have basically the same display, read-only display that's seeing what the telescope operators are seeing. So we're seeing, the operations of what's going on. But if they want to talk to the scientists, then I escort them up to the console where the astronomers are sitting, and we plug in our headsets and talk to them. And yes, so I try to, we have our home base of our own console, but we try to circulate around and ask everybody. One of the important lessons that they're bringing back to their students is the wide variety of experiences and careers that brought people to be part of the Sophia mission, and not just astronomers. There's very few astronomers, actually, but people who've done all sorts of things, and now they're part of this mission. And so the teachers can bring back to their students that you could picture yourself in this scene. So I have the teachers talk to everybody who's on board. That's probably 20 people normally in a normal situation. Ask them what they're doing, how they're doing it. I'm supposed to make sure that somebody's not sweating bullets when a teacher comes up to ask questions, right? Be sensitive to whether there's a crisis going on. But anyway, we monitor what's going on. They ask the astronomers how they designed their experiment. They talk to everybody about what's going on.
Neko Girl is asking in the chat, how is Sophia stabilized? How do you stabilize a telescope like that on the side of an airplane?
The telescope, 17 tons of telescope, is floating on a bearing, a double sphere with a hydraulic fluid layer between the two spheres. So the vibrations of the plane are mostly damped out. They're not really affecting the telescope, but also there's a software feedback where we have a visible light guided camera that's looking at either the target or a nearby fiducial star, and there's a software feedback loop that keeps us pointed at, takes out the whatever residual vibrations there are. So the telescope is pointed sort of by the plane turning partly, then the fine tuning is with this guider system, and the telescope is floating. That's the medium short answer.
And I know that for for astronomy and for infrared observatory, I mean, obviously a space telescope that big would be lovely, but how does this compare as an airborne observatory compared to, say, a ground-based large telescope, infrared telescope, like something you might put in Chile?
Couple of points. It's almost exactly the same size as Hubble. It's a 2.5 meter diameter telescope. The ground-based observatory, even at a high site like in the Andes or on Mauna Kea, cannot receive far infrared radiation. It does not get through the Earth's atmosphere's water vapor. Mm-hmm. So Sophia, by being above the atmospheric water vapor, can have access to a region of the spectrum from about 30 microns wavelength to 300 microns wavelength that you cannot do from any ground site. at all. Don't matter how big the telescope.
Right. So this is literally a wavelength that we just cannot access from down on the ground.
Right. So you could think of Sophia as a low-flying space telescope.
Yeah.
We're able to do 80% of the acuity of the access to the infrared wavelengths that a space telescope would.
Yeah. It's surprising too, and one of the real advantages of a ground-based telescope, or in this case an airborne telescope, is just the fact that you can upgrade it, you can switch out the gear on it, you can continue to improve it without having to send the space shuttle and $1.5 billion and astronauts and train them, and
exactly.
As what we saw with Hubble. Have there been plans to build other airborne-based observatories? It seems like a pretty good sweet spot for this. I know
this is the third and the largest. There was a Learjet with a 10-inch telescope. Then there was the Kuiper Airborne Observatory that was a 36-inch telescope in a C-141 cargo jet. And then Sophia is now a 2.5-meter telescope in a 747. And Sophia is too young in its career for the people to be thinking about the next step, but it's this is the widest body aircraft that we could buy in 1996. So to put a bigger telescope than this, you would need a much bigger airplane. We didn't build the planes. Wasn't custom made for this. It's an airliner.
Right.
It's a United Airlines airliner that we bought, and chopped.
So later on, I don't know, like an Airbus or something. There's not much that's bigger.
Right.
Than a 747.
Yeah, that's right. Yeah, someday.
Yeah, someday.
Well, a balloon could potentially carry a bigger telescope to a higher altitude. Yeah.
And I mean, I know that there's a ton of balloon-based missions as well as suborbital rockets if you're willing to only look at something for about 2 minutes before your rocket comes back. But I think it's it's very creative. I think it's a really great platform for a lot of astronomy. It really is that nice balance between a giant ground-based observatory that still has to deal with all of the atmosphere, but a space telescope, it's as you say, as close as you can get to being in space. Over the course of an evening, is Sophia looking at a bunch of different targets?
Yes, so usually 6 to 10 targets would be typical in a night, and they would be from multiple different astronomers' proposals. So it's not when I was being a graduate student or a postdoc and doing ground-based astronomy, usually you'd have the telescope to yourself for the whole night for whatever your projects were. In this case, we're interleaving half a dozen different astronomers' projects on a given night, right?
Yeah. And so and in this case, often the airplane itself changes its trajectory depending on what target is being looked at with that zigzag.
Each it's a zigzag all over the Eastern Pacific and the Western U.S., and each zig is a different object.
Right. And so I'm assuming the planning in advance is very complicated. What are some recent discoveries that Sophia has participated in that maybe people are familiar with?
One of the big ones in the last year was that Sophia detected in the interstellar medium the molecule that's inferred to have been the first molecule to have formed after the Big Bang. So there wasn't spotting this molecule, helium hydride. By the way, your high school chemistry teacher told you that helium doesn't make compounds. Yes, it can if you push on it hard enough. So helium with a proton added. That molecule would have been the first one to form as the universe cooled after the Big Bang, and was detected by Sophia in a planetary nebula context. So doing checks on cosmology by looking at nearby objects, that's one of the ones that comes to mind first.
Neil Yu is asking, is Sophia always above the weather?
Yeah. Oh, well, yes, above clouds and water vapor layer, although we get turbulence, and then in the situation where we have to strap down, so does the telescope. So we stop working for, however long it's bumpy, but above clouds, almost entirely. Yeah. Mm-hmm.
Yeah. So again, it's kind of like your own weather machine, while astronomers at the mountaintops are stuck with whatever weather is passing through their system. Yeah, you're able to just fly above it and ignore most of it, which I think is just incredible. Fantastic. So once again, Dana, if people are teachers, who is this open to?
Any U.S. Citizen or green card holder who has their district work out a memo of understanding with the SETI Institute. Right now we have 13 active districts in 8 states, and we're happy to add more.
Fantastic. And again, if people want to apply, where should they go?
Then we'll work with their district to shepherd them through an application process, which is usually open in the fall, and then we have a peer panel review the applications. So the district will do all the PR and that kind of stuff.
But right. SETI.org/AAA. Right.
Yeah. SETI.org/AAA. So the application opportunities get announced there. Instructions, criteria for applying, and so on are SETI.org/AAA.
Right. Well, again, thank you so much for taking the time to chat with us. And you're going to stick around and join the Peanut Gallery as we talk about different topics in space and astronomy. Feel free to jump in if any of these personally resonate with you as we move through them. So, all right. Thank you again. And anyone, that sounds like an amazing opportunity. So if you're a teacher, if you are an educator, you live in the U.S., get on this. What a great opportunity. All right, Chris, tell us what you got.
Well, I bring news from the early universe. So I guess I'm kind of the galaxy guy here. So galaxies come in all shapes and sizes, but overall they do have some categorical consistencies in those shapes and sizes and in their structures. And so we call this galactic morphology. And so the common features of galactic morphology are like spiral arms or bars, but you also get this rare bunch of galaxies that have some striking features. And one of these odd groups are known as ring galaxies. And right behind me, I have an example of a ring galaxy. So this is the Cartwheel galaxy, one of the examples of a ring galaxy in our local universe. And so one of the big discoveries that happened earlier this month was the first discovery of a ring galaxy from the early universe. And so this work was done by Dr. Yuan. She's part of the ASTRO 3D group, which is a government-funded research initiative from Australia. And so part of this work is they were looking at disk and spiral galaxies from the high redshift universe, so a redshift beyond 2. So that's at most 3 billion years after the Big Bang. And so they had this survey of these disk spiral galaxies, and there was one of them that sort of stuck out among the group, and there was a follow-up analysis using optical data from Hubble and spectroscopic data using Keck. And it was really the confluence of all these sources that they find that this is actually an example of a ring galaxy in the early universe with beyond a redshift of 2.
All right, we're going to show this cool video.
Right, and so the article has this great example of how you get ring galaxies. So like as the video is playing now, so you see this sort of smaller galaxy colliding head on with the host disk galaxy, and you get this propagating density wave that goes out in the plane of the disk. And so this is how you form ring galaxies, and it's through this formation mechanism that results in ring galaxies being exceedingly rare in the universe.
And so, just looking at the shape of that collision there, like it clearly just made a punch right through the center of the larger spiral galaxy. And so that's the key. Like in every other kind of interaction, you're going to get them tearing each other apart and sort of causing all the star formation and whatever, depending on the size. But in this case, you've got this bullseye, just one galaxy punching right through the center of the other one and kind of knocking out its center and causing those density waves.
Yep, that's exactly it. So usually when you have these collisions, there's always like the complicated angles. It may be the galaxy may be swiping and all that. So how you get a ring galaxy is very simple. Like you have this thin spiral galaxy, and then you have sort of a perturbing object going straight through the center, causing those propagating waves.
And so why was that so surprising to see early on in the universe?
Right. So the reason why this is so interesting, at least in my view, is if you have ring galaxies early on in the universe, that must mean you have those massive thin spiral galaxies to begin with for that to occur, because the ring fraction, so that the number of ring galaxies you have in the local universe, is about 1 in 10,000 galaxies. And the reason why is because that interaction that we're talking about, having a galaxy going straight through, is pretty rare. And also these structures that you get the rings are short-lived. So you have to catch it at the right time, and you also have the right you also have to have the right reaction.
And I mean, is it surprising that the galaxies themselves, like you need to have a fairly mature spiral galaxy to even have this kind of shape? And so it's sort of like the key to be able to see this is you had to start with a galaxy that was already fairly well developed that early on.
Right.
Otherwise you wouldn't get that kind of a structure. So it's almost,
right.
It's fun. It's interesting to be able to see, you can just see the wreckage and then be able to know almost like the history of everything that happened up until that point. I mean,
So the thing that I think is the next step, and what I'm really interested in, is what is the ring fraction through cosmic time. And so if you had a point in the early universe where things were more compact, where merger rates were more common, does that translate into a larger ring fraction? And so one of the conclusions from this paper, even though they only have one discovery, based on the volume of galaxies that they surveyed, is that they find a constant ring fraction, or in other words, the ring fraction in the early universe seems to be about the same as the ring fraction you're getting now. And so that may sound counterintuitive at first, because if you would expect if there were more mergers, then you should have a higher ring fraction. But what determines the ring fraction is not only the merger rate, but also the prevalence of those massive spirals.
Right.
And so those two forces are sort of acting in concert that give you the ring fraction. And
right.
so you can sort of use the ring fraction as sort of a proxy for galaxy assembly and for the prevalence of spiral galaxies in the universe.
And I guess that was my next question was can we use this to probe the structure of the early universe?
Well, yeah, that's the goal there, because the ring fraction has encoded in it those two interesting features of galaxy assimilation, which is the merger rate and the prevalence of those thin, massive spiral galaxies. And so that's why I think in sort of researching further, the ring fraction is really important for galaxy evolution and for the history of hierarchical accretion and so forth.
I mean, are there other objects like that you would see early on in the universe at the very limits of what Hubble is capable of seeing? Like, I know they're like seeing Einstein rings gives you a natural telescope to see farther into space than you could normally, but it doesn't necessarily decide what it is that you're going to be looking at. But you see something like this, it just gives you a pile of information about what happened going on in the early universe. Are there more of this kind of thing?
Right. So it's interesting because ring galaxies are they're purely a dynamical effect, and so just from seeing it, you can sort of infer this whole sort of rich history of the environment and so forth. So there are other dynamical features you can look for. So one of them is tidal streams. So if you find these streams of stars sort of in the halos of these galaxies, that's also indicative of a past formation history, which tells you more about the environment the galaxy lived in. There's also shells, which are kind of like rings, but they're hard to envision. But sort of like these shells propagating from the center of the galaxy, that's also indicative of past accretion events. And so there are all these tiny minor morphological features of galaxies that sort of give you an inkling of where they're coming from and have implications for the cosmology.
Arjun is asking, could this lead to galaxies losing their supermassive black holes? It looks violent.
Ooh, interesting question. tentatively, I would have to say yes, right? Because if you had like this massive object going straight to the center, that should certainly shuffle up what's happening in the core of the massive galaxy.
Yeah. Well, there you go. There's your next paper. Awesome, Chris. That's absolutely fascinating. I love this kind of thing because it's both this really cool extreme event, but also a very useful tool for measurement, which is like my favorite thing. Just galaxies crashing together, but also yardsticks.
And nice to look at.
And really great. Well, the one in Chris's wall for sure. The the ones that are far away are these little smudges. All right, Beth, we're going back to Neptune.
Yes, we're going back to Neptune. It's about time. So this week, NASA Jet Propulsion Laboratory announced that they've submitted an entry into NASA's Discovery program. This program allows scientists and engineers to put together a team, submit a proposal for a potential planetary science mission. And in this case, they've entered one that they've called Trident. There's a joke here. I'll get to that. Amazingly, this is not a backronym of any sort.
Okay, yeah, just Trident.
Just Trident.
Yeah.
But the reason for the name, aside from the fact that it's Neptune and Neptune's symbol is a trident, they're taking a three-pronged approach to this mission. So
that's like a backronym.
It kind of is, yeah.
Yeah.
Yeah. So what they want to do is their goal is to spend 13 days at Triton, which is Neptune's biggest moon. Basically, they looked at images from Voyager 2 that are 30 years old and said, we need to go back because Voyager saw icy plumes coming from Triton's surface. And of course, we're all about those icy plumes right now, and it's all very exciting. And there's a couple other things that are weird about Triton. Triton is rotating. Its orbit goes the backwards direction from Neptune's rotation. Yeah. So that's one thing. The surface looks really young and fresh. There's very few craters. And I mean fresh by geologic timescales. So they want to send a mission back, and they want to basically spend a couple weeks taking pictures, running instruments, and they want to figure out what's going on with this moon and if there's actually an ocean underneath, like we've seen with Enceladus and Europa, what's causing the resurfacing. And also it has a very active ionosphere that's kind of surprising considering how far it is from the sun. So they want to find out what's going on that causes that to happen.
I mean, it's funny, we're all so familiar with the geysers on Enceladus and the similar features on Europa, but I think Triton was like the original place where these kinds of features were discovered. Back in 1986, they first saw these hints of these geysers in the pictures they were taking of Triton. And so it's kind of surprising to me that it hasn't been as high a priority. I guess it's because it's harder to get to than Europa or Enceladus. But 13 days at Triton. Can you explain the flight path? Because that sounds a little funny that you would go there, but then you would only stay there for 13 days.
I'm not actually sure on the flight path when there. So basically, and this is one of those, Pamela would hate me talking about a mission that hasn't even been selected, let alone launched. But
she's not here.
I know. The proposed launch date is October 2025, with a backup of October 2026.
That's so soon.
I know.
2025 is not long.
Yeah, but it takes advantage of this once in a 13-year window for an alignment with Jupiter, and then it would get to Jupiter in 2038.
To Jupiter?
So, yeah. Well, it would get to Triton via Jupiter.
Via Jupiter.
Yeah,
okay, so so it would do a gravitational assist at Jupiter and then get out to by 2038. But a 13-day encounter, it just seems weird to me. Like, is it a flyby?
It didn't seem like it was a flyby, but I couldn't find any information in there on what the orbit is.
What? Does it remain in the in the orbit? Like, I'm confused now. I hadn't gotten this far. I just saw.
Yeah, I couldn't find any information on what the actual orbit was. It just said 13 days at Triton, and I'm like,
does anybody know that? Or okay, there you go. Dana is saying it is a flyby. Yeah. Okay. So like think New Horizons.
Yeah, but a bit more time.
Sure. Yeah. Yeah. Well, but I mean, I don't know though, right? Like if it's going to be a flyby, then you get one shot. You get a bunch of pictures as you're coming close, and then you like, are they just measuring 13 days of when you start to see it on the horizon to when you get close-up pictures? And I'm assuming they're going to take pictures of the part that they haven't seen. I mean, I'm excited, but
there are cameras involved, so that's exciting.
A flyby has been done. It's time to send an orbiter. So I'm with you. I'm
of the belief every gas giant needs an orbiter.
Yeah. I'm gonna wait for a better orbiter. I think I'm gonna wait for a better mission. But still, I mean, yes, I'll take a flyby of Triton if necessary. If that's all we get. I mean, these are these tiny little discovery programs. They'd be all right.
Can you just imagine like a high res image of Neptune though?
Oh yeah, yes, please. Yeah. So do the same. Like grab more Neptune images with the modern equipment, and modern, and nice high res images of Triton and hopefully some other moons as well as it comes through the system. But Cassini has spoiled me so much, right? Just around and around and around, right? Just taking image after image.
Such an amazing mission.
Yeah.
I miss Cassini.
Yeah. Yeah. That's all I can think about. But still, okay, fine. I'm excited. Thanks, Beth. All right, Brian. Cosmology. It's all wrong.
Cosmology and what we don't understand. So this new study is looking at what we call the standard model of cosmology, which is sometimes called the LCDM model. CDM stands for cold and dark matter. L stands for lambda, which is a symbol in the general relativity equation that describes the universe as a whole. Lambda is basically the cosmological constant that Einstein first introduced to keep the universe stable, and then became related to dark energy and the Hubble constant. So to understand the model, we really kind of have to know what the value of this lambda is. And if you know the value of the Hubble constant, then you know lambda. Or if you know lambda, you know the Hubble constant. So it all comes down to trying to measure what this Hubble constant is. And the Hubble constant determines the rate at which the universe expands. Basically, the structure in space and time causes the universe to expand at this certain rate that's related to the Hubble constant. And there's several ways that you can measure what that Hubble constant is. The original one is to look at things like Cepheid variables in nearby galaxies and look at their Doppler effects. So they're moving away from us at a certain distance. Their light is redshifted. And then you can use variable stars to find out how far away those galaxies are. Well, this is continued all the way out at ever greater distances to things like supernova. A type 1a supernova is a standard candle. If you know its brightness, you know from its apparent brightness what its actual brightness is. You can find the distance, and then you can measure the redshift, and that's how you find the Hubble constant. It is basically a ratio of distance and redshift. So the supernova way is kind of the way that won the Nobel Prize. It's the way that we kind of think of measuring the expansion of the universe. But there are other ways, and one of them is to look at, say, the cosmic microwave background. So this background heat left over from the Big Bang has little variations in it. And the scale of those variations, as we see them now, depends upon how much the universe has expanded since that initial hot dense state. So if you look at the scale and see where are the most scale of fluctuations, at what size are most fluctuations, you can find out, oh, well, that means that the universe has expanded this much, and then you can find out what the Hubble constant is.
Right.
So that's all fine and good. If the standard model is correct, these two values should give basically the same result. And it's turned out that as we've made ever more precise measurements, they have become ever more in disagreement. So basically, if you look at the cosmic microwave background, it gives a value of about 68 kilometers per second per megaparsec, which means that's the speed at which you're gaining in the expansion for a megaparsec of distance. If you do the supernova measurement, it comes out to about 72. Now, early in the day, their uncertainties overlapped, so that wasn't a problem, but we're kind of getting to this where they don't overlap anymore.
Yeah, we've talked about this several times in the past, right?
We've talked about this several times.
Yeah,
and of course, what I would always say is what we need are more ways to measure this.
Right.
We need new ways to measure this. Well, it turns out that there is a new way to measure it that's been published, and it uses a completely independent way from the other two.
So let's explain the way first before we get to the result.
So the way it's done is to use what's known as a astrophysical maser. So more people are familiar with laser, light amplification by stimulated emission of radiation. Maser is microwave amplification by stimulated emission of radiation. It is a microwave laser, and it's emitted by water. Basically what happens is that when water is orbiting something like a black hole, a supermassive black hole in the center of a galaxy, it gets excited, and it's in just the right configuration that it triggers a cascade. So you get this stimulated emission of water microwaves, and it just happens naturally, whereas here on Earth it happens in a lab. The nice thing about that is that because it's a laser, basically, lasers have a monochromatic color, so they're a single color, and they're very coherent. So they basically emit light at a very precise wavelength.
Right, and so we're seeing a laser. The color is the color of water in microwaves.
Right.
Yeah.
Basically. So what happens is you can then, because you know that this is water vapor stuff, this is water laser or water maser, you know what that wavelength is. So you can measure the redshift from that galaxy and that supermassive black hole in the center of the galaxy. You measure that really well. So you've got the redshift.
Okay. And
that's one thing.
Right, but I mean, we were already measuring the redshift to galaxies. This is what Hubble did, right? To be able to measure the redshift to the Cepheid variables. So how is this more accurate than the Cepheid variables?
It is somewhat more accurate, but the real key is that you not only have to have redshift, you also have to have some way of doing distance. And usually distance is things like variable stars or supernovas or things like that. What's nice about this is that this material is orbiting the black hole. So as it's spiraling around, one edge of this accretion disk is coming towards us and is blue shifted a bit relative to the overall redshift. So it's less redshifted, if you say.
Right.
On the other end, it's moving away from us, and so it's redshifted.
Compared to the overall redshift of the entire galaxy. Right.
So basically you get the whole thing is redshifted, and one side is a little bit less redshifted and the other side is a little bit more redshifted. So if you actually look at the signal, what you get is you get a triple peak.
Right.
And it's very easy to identify, but you can make then a very precise measurement of how fast this is rotating at different distances. So that means that this is close to the black hole is moving this fast, out here it's moving this fast, out here it's moving this fast. So you can actually find exactly what the size of that emission is with the lasers.
And you can pinpoint essentially the absolute center of the dead center of every galaxy that you want to look at.
Right. But if you know then what the actual size of that accretion disk is, and you compare it with the apparent size in the sky, you're now using size to measure the distance.
Right.
It's just like looking at a tree. If it's always the same size, you know how far away the tree is because you know how big it is.
Okay, and then you're comparing that with the redshift to make sure the two match up.
Right.
Right.
And so what you get is you get both size and redshift all from water masers.
Wow. That's incredible.
Completely independent of the Doppler of the galaxy supernovas and completely independent of the cosmic microwave background.
All right. So now we've set up the methodology. And so this sounds like a very accurate way to decide who's the winner, and the winner is
neither. The CMB says 68. The supernova method basically centers around 72. This method centers around 75, 76.
Wow.
Could be as high as 78. So it's even higher. It's basically, this new result has made everything worse.
So it is not splitting the difference. It's not saying, okay.
It's not splitting
no.
the difference, and it's not agreeing with one or the other. It's saying you both are all wrong.
Brian, what's the error bar?
It is, I want to say it's, let's see, it's 3.5 on either side. So basically the 72 and this result, the supernova and this result just overlap. They just barely cross, but the best value is way outside of that. So you can say they agree, but yeah, they agree like a freshman physics lab agrees.
Right. So
yeah, I got an overlap, I'm counting it.
So when we consider the distances these are measuring, right? The cosmic microwave background radiation, that's measuring the very beginning of the universe, 13 point, I guess now it doesn't matter. Who knows how far away that is? Not 13.8, some number that could be more or less than 13.8. But then you compare that to the supernova, they're more recent. Where do these masars sit on the time spectrum of the universe?
They're in the same basic range as the supernovas. They're not quite as far, but one of the problems is that because you had the CMB and then you had the supernovas, you could argue, well, maybe it was different over time. The CMB is a really far distance, and the supernovas, although they're billions of light years, are closer.
Yeah.
Well, this new method is in the same range. And so they overlap in distance and they don't agree.
Right.
So there isn't a resolution for them.
Right. But I guess if you've got two methods, both of which are fairly accurate, both of which are attempting to measure the same rough period of time, that seems to lend support to the idea that maybe, we talked about this again a couple of weeks ago, this idea that maybe it's the type 1a supernova that in fact we don't understand them as well as we thought we did. Now we understand this, right?
Right, but there was another one that I had actually written about a week before that was even a fourth method that was using basically the scale at which galaxies cluster.
Right.
It's called the baryon oscillation. And so what you get is a scale of those. Basically, as the universe expands, galaxies tend to cluster, but the gaps between them get bigger. By looking at the overall scale of that, you now have a measure of the rate of expansion. That one falls that's even closer. So it was even a shorter distance into the galaxy, into the universe. And it was in between the CMB and the supernova one.
Okay.
So it doesn't agree with this either.
Okay, so what's the explanation then?
Wait, there's also another method you can.
Oh,
you can
sure,
use.
yeah. Fifth.
There's a couple of others, yeah.
Yeah.
Go ahead.
Wait, you can use so this one was sort of used after the neutron merger discovery with the gravitational waves. Because if you have a kilonova, that gives you can get a redshift from that, and you can get a distance from the gravitational waves. And so if you have the redshift and you have the distance, you can solve for the Hubble parameter that way.
And if we get to more observations at farther away, I know with some of those future observatories, we'll eventually turn up every kilonova explosion in the observable universe. Suddenly you've got a completely independent multi messenger method of calculating. That would probably solve it once and for all, wouldn't it? If you could measure all those kilonovas going off.
What's really happening is that as we're getting more data, it's getting worse. Because it was basically, we're going to have different methods. There's like half a dozen measures of doing this.
Yeah.
And they're all kind of all over the map. And what's happening is we're getting more data, which is great. But what's happening is that all the uncertainties are just getting smaller.
Yeah.
We're not getting this kind of, we were actually supposed to be here.
Yeah.
What we're getting is this. And
Yes.
now not only do they disagree, they now disagree harder, which is really problematic for understanding things.
Okay, so what are the creative ideas that astronomers are coming up with to explain the diverging results?
The I mean, it starts getting really kind of crazy in the ideas that people are coming up with. So maybe it's axions, maybe dark matter is somehow connected to dark energy. So they're two sides of the same coin, and in the model, they're fouling each other up. You know, it could be that there are, so somebody's proposed like quantum fluctuations that would affect the rate of shift from the light. You're basically kind of going into, let's throw out a whole bunch of standard physics and come up with other whatever wild idea we can come up with.
I mean, it sounds to me like before the more recent accumulation, like if you just have the two measurements, the one at the beginning and the one at the end, they're different rates, then the answer is, oh, then it's just changing. That it was this rate at the beginning and now the rate is changing now, and there's like some kind of smooth change from the beginning to the end. That's easy-ish to wrap your head around. But the fact that multiple methodologies, which are very accurate, that are measuring the expansion rate of the universe at the same time in kind of different ways, they're not agreeing, and yet they're all very accurate. And so you can't come up with a simple explanation of, oh, it's just that the speed of the universe goes up and down. It's something weirder.
Right. So if the speed of the universe goes up and down in different parts, then the cosmological constant and Einstein's idea is absolutely wrong. That you can't have that within relativity.
But Einstein was right. That's something that we always say.
That's one we typically say. But, you know, there could be things like, there could be a fifth force, so what they call quintessence, that is some matter that gives off properties of energy in the same way that dark matter gives off properties of gravity. You know, we see the effects of dark matter from gravity. We could see the effects of this from dark energy.
So then, I mean, if I was to come up with a theory to try to explain this, what little boxes would it need to check?
It would need to, right now, it would need to account for why different measurements, why different methods give dramatically different results. And also, from what we can tell up to this point, why they don't have these dramatically different speeds in different directions.
So it would need to explain. So it would need to explain why masers work differently than supernova explosions, work differently from gravitational waves, work differently from the cosmic microwave background radiation. That isn't it just speeding up and slowing down, because it would literally have to explain each of these observations, why they look the way they do, to come up with a number.
Right. One way to do it is to say you would have to explain why light behaves differently than light.
Why light behaves differently than light.
Okay, that one actually broke my brain.
Yeah.
Because microwave lasers are just light.
Yeah.
The redshift should be exactly the same as it would be from the light of galaxies. And we can do those from distinct energy levels, so that should be exactly the same. You can tweak supernovas a bit, but we know that there's a limit to how much you can tweak them.
Right.
The microwave laser optical size is straight out of relativity. So you got to throw relativity out if you're throwing that out.
Right.
You know, the cosmic microwave background is a pretty standard and robust model. So you'd have to throw parts of that out.
Yeah. Could it be dust? Can I just answer this right away and just say that it's dust?
In this case, it can't be.
Oh, because it's usually dust. It's always dust.
Because in this case, not only is the light a single color, it's a single wavelength, it's also coherent. So the scattering takes on a whole different polarization character and stuff that you can account for. So this is a very nice way of measuring cosmic expansion.
Yeah.
And it doesn't rely on a supernova model. You don't have to assume that there's a standard candle, because you're not doing brightness, you're doing size. And the dust, even though it could affect the brightness, won't affect the size. And the size is straight out of gravity. So it's just, this stuff is moving this fast because it's in free fall.
So if you had to place your bets today, what do you like? Or is there just nothing?
It's hard to say what I like, because what I want to see is, I want to see the radical theory.
Yeah.
If it's quintessence, then that means there has to be something, just like dark matter has to be some other particle that isn't part of the standard particle physics model. There has to be something else, whether it's axions or sterile neutrinos or something. Dark energy would have to be something else yet again. It would have to be a whole new thing. That excites me because it would point us to a direction of radically different physics.
Yeah. Chris, this is in your wheelhouse too. What, place your bets?
I honestly don't know. I think I'm with Brian in the sense that I would love for all the physics to be upended within my lifetime. I'm sure that'd be great for my career, and also because like the implications of this also they trickle into like all of cosmology as well, like how we build how structure forms. It's because it's also dependent on our choice of Hubble parameter and on the choice of dark energy. So if you throw that stuff out, this also has huge implications for how we think like galaxy clusters form, like how galaxies, like the time scales when galaxies form. And so if you pull the card out from the bottom, like all the entire house.
Right. And as you say,
I'm glad to be alive. I'm glad to be alive during this time.
That's the thing that I always find so funny, is that people always say, oh, astronomers, it's like a religion. They just like, they don't have no reason, and they don't want to be challenged in their theories. But you guys are giddy. I would describe you guys as giddy right now at the possibility of exciting new ideas in cosmology and astronomy, and an opportunity to see some fresh ideas. Which is the exact opposite, I think, from what people expect. Dana, I'll give you a chance to weigh in too. Place your bets. Oh, you're muted.
I'm muted. I don't think there are enough data in the Maser thing to rival the huge amounts of data in the other two categories, and so I wouldn't give it as much weight as the other two.
So you think that Einstein was right? You're still right.
I think
Yeah.
I'll put my bets on Einstein. Yeah,
it has been a pretty safe bet for a long time, so it does make sense. Fantastic. Well, guys, I really appreciate that. Beth, I don't know. Do you want to have a take as well?
I'm going to stick with Einstein.
Einstein was right.
Every time someone sends me some email about Einstein is wrong, I just kind of laugh and go, "Yep, okay."
Yeah, and mark my words, it's dust. All right, Beth, you're on my screen. If people want to, what are you working on? Where can people find out more?
Tonight we are hosting, the Study Institute is hosting a virtual talk on planetary defense and asteroids. So you can go to study.org and click on that link. I think we still have some reservation spaces available to watch it. And you can find me pretty much everywhere on social media at Planetary Pan.
Fantastic. Chris.
You can follow me on Twitter at @TheRealCCar. I haven't been doing much lately because the world is kind of shut down for the moment, but I promise at some point in the future I'll be active again. So follow me on Twitter.
Fantastic. Brian.
You can find me on Universe Today, where articles go up. You can find me on Twitter at Brian Koberlein, and you can find my own website at briankoberlein.com.
Fantastic. And Dana, you stuck around, so let people know where they can find out more about what you're working on.
The Study Institute website has a list of their scientists, but and some of my articles, but also on YouTube there are 2 lectures I gave at the Silicon Valley public lecture series, and I think, yeah. And also, if you look at Sophia Airborne Observatory, Airborne Astronomy Ambassadors on YouTube, you will find recordings of several of our teacher groups and what they were doing and what they had to say. And I'm in the background.
Fantastic.
The teachers were in the foreground, as they should be.
Excellent. All right, I'm going to put everybody back up on the screen. I've got a new QA coming out tomorrow, as well as an episode on Proxima Centauri's planets coming up at the end of the week. So stick around for that over on my YouTube channel. And then another star party on Sunday night. So if you want to see live views of the night sky, come and join us on my YouTube channel. All right, thanks everybody for joining us. Thank you to all the moderators, both on Twitch and on YouTube. We really appreciate this. We couldn't do this without you. Remember, go to the Weekly Space Hangout crew, wshcrew.space. And if you enjoyed this episode, give it a thumbs up. I never nag for a thumbs up, but I thought that was a particularly great episode all around, and so I think you should give it a thumbs up. All right, thanks everyone, and we will see all of you next week.
Bye-bye.
Bye.